In this unit, we're going to be talking about synchronous motors and their controllers. Synchronous motors have several features. They operate at a constant speed, and they can be used to improve the electrical efficiency of an industrial operation. They're often used to drive air compressors and fans or other equipment that require constant speed or high mechanical power at low speed. Like all motors, synchronous motors have two main parts: a stator and a rotor. Basically, synchronous motors operate by using three-phase alternating current in their stators to produce a rotating magnetic field. The rotor of a synchronous motor has electromagnets that lock in with the stator's field, so that the rotor turns at the same speed as the stator's rotating field. The stator of a synchronous motor is the fixed or non-movable part of the motor. Inside the stator's frame are conducting coils or windings that are set inside the slots of a steel core. Three leads from an AC power supply allow three-phase alternating current to flow through the stator coils. The stator coils are connected in pairs, and when current flows through a coil pair, a magnetic field is produced between the coils with a north and south pole. The magnetic poles produced between the stator's coils are called the stator poles. In a two-pole synchronous motor, there is a coil pair for each phase of three-phase alternating current. As each phase of current flows through its coil pair, it produces a magnetic field with a north and south pole. Here the magnetic poles are represented by the colors green and yellow. The strength of the magnetic field for each phase increases and decreases along with its current, and its magnetic poles reverse when the alternating current changes direction. The net result is that a rotating magnetic field is produced in the stator. The speed at which the magnetic field rotates is called synchronous speed, and a synchronous motor is an AC motor that operates at synchronous speed. The synchronous speed of a motor depends on two things: the frequency of the current flowing through its stator coils and the number of magnetic poles in its stator. A synchronous motor is supplied with a current that alternates at a constant frequency. But not all synchronous motors have two magnetic poles. Synchronous motors can have 4 or more magnetic poles in their stator. In fact, synchronous motors often have as many as 32 stator poles. The more magnetic poles in the stator of a motor, the slower the stator field turns. So the stator field of a synchronous motor that has 4 poles will turn about half as fast as one with only 2 poles per phase. Since a synchronous motor operates at synchronous speed, the rotor of a synchronous motor turns at the exact same speed as the stator's rotating magnetic field. Now, in order to understand how the rotor does this, we need to take a closer look at a typical rotor of a synchronous motor. A typical rotor has insulated coils or windings that are wound around steel projections. The projections with their windings are often called pole pieces, and when direct current flows through the rotor windings, the pole pieces become electromagnets with fixed north and south poles. The number of magnetic poles on the rotor of a synchronous motor equals the number of magnetic poles in the stator of the motor. Direct current is generally supplied to these rotor windings from an outside power supply through slip rings and brushes. Now, when a synchronous motor is first started, the stator's field immediately rotates at synchronous speed. The rotor, however, is a physical object and must overcome resistance to its rotation. It's therefore impossible for it to immediately lock in with the stator field. So, in order for the rotor to lock in with opposite poles in the stator's field, the rotor must first be accelerated to a speed close to synchronous speed. To accelerate the rotor, a small DC or AC motor is sometimes used. A more common method, however, is to have conducting bars called amortisseur bars on the rotor. Amortisseur bars operate on the principle of induction and allow a synchronous motor to operate as an induction motor until the rotor reaches a speed where it can lock in with the stator's rotating field. When amortisseur bars are used on a rotor, They are positioned so that they are parallel to the shaft of the motor. Amortisseur bars are shorted at each end to allow a complete circuit for current flow. Here's a simplified version of a rotor for a synchronous motor with amortisseur bars on it. When the motor is first started, the stator field immediately rotates at synchronous speed. The rotor, however, is unable to lock in with the stator's rotating field. But relative motion between the rotor and the stator's field causes a voltage to be induced in the amortisseur bars. The induced voltage causes alternating current to flow through the amortisseur bars, and a magnetic field is produced. The amortisseur bar's magnetic field interacts with the rotating field of the stator and causes the rotor to turn. As the rotor accelerates, relative motion between it and the stator field decreases. When the rotor reaches a speed close to synchronous speed, the rotor windings are energized with direct current. The rotor pole pieces become strong electromagnets and lock in with opposite magnetic poles in the stator's rotating field. The rotor then turns at synchronous speed. Once the rotor turns at synchronous speed, there is no longer any relative motion between it and the stator's rotating field, so induction into the amortisseur bars no longer occurs. Well, we've shown how a synchronous motor operates at synchronous speed. In the next segment, we're going to show you what occurs when load is added to a synchronous motor and what happens when the strength of the electromagnetic field of the rotor poles is varied. We're also going to show you how a synchronous motor can be used to improve the electrical efficiency of an industrial operation. But for right now, take the time to review this information in your text. In the last segment, we saw how the stator's magnetic field rotates and how the rotor of a synchronous motor is made to turn at synchronous speed. In this segment, we're going to show you what happens when load is added to a synchronous motor and how synchronous motors can improve the electrical efficiency of an industrial operation. Now, as any motor, synchronous motors are designed to handle a certain amount of load. When load is placed in a synchronous motor, the rotor tends to turn slightly behind the stator's field. In other words, the rotor tends to lag behind the stator field. The rotor, however, is still locked in with the stator's field and turns at synchronous speed. But if a load is placed in a synchronous motor that is more than the motor is designed to handle, the rotor will pull out of synchronization. We can demonstrate this effect of load on a synchronous motor by using a strobe tachometer. A strobe tachometer is an instrument that allows the speed of a rotating piece of equipment to be measured without touching the shaft. You may already have seen the effects of a strobe light on moving objects. If you have, you've seen how the flashing of a strobe light appears to stop the action for a moment. Well, a strobe tachometer gives a similar effect. It uses a strobe light and has a dial to adjust the number of times the light flashes in a minute to the number of rotations per minute of the equipment being measured. We'll mark the shaft of this synchronous motor with white paint. The mark will serve as our reference for rotor rotation. The strobe light will flash on the mark each time it completes one full rotation. When the strobe flashes on the mark will appear to be still. Since this synchronous motor turns at 1800 revolutions per minute, we'll adjust the strobe tachometer dial to 1800 flashes per minute. The synchronous motor is started. It accelerates by induction and locks into synchronous speed. Notice where the mark appears. Now we'll add load to the motor. Watch the mark very carefully. The mark appears to move backward, but the speed of the stator's field and the rotor haven't changed. They're both still turning at 1800 revolutions per minute. The change in the position of the mark, therefore, indicates that the rotor is lagging behind the stator field. Remember, although the rotor is lagging, it's still making 1,800 revolutions per minute. If we continue to add load, the mark moves backward further, and if the load becomes greater than the motor can handle, the rotor pulls out of synchronization. Rotor lag also occurs when the strength of the rotor's electromagnetic field is decreased. The electromagnetic field in a rotor is generated by direct current flowing through the rotor poles. The current flowing through the rotor windings is called excitation of the rotor. By decreasing the direct current flow through the rotor windings, we underexcite the electromagnetic field. In other words, the field becomes weaker. By increasing the direct current through the rotor, we overexcite or strengthen the electromagnetic field of the rotor. We'll use the strobe tachometer again and see what happens to rotor rotation when we underexcite the rotor's electromagnetic field. We'll use the same synchronous motor that we did in the previous demonstration. This rheostat controls the flow of direct current through the rotor windings. By adjusting the rheostat, we can decrease the direct current flow through the rotor. The amount of current flow through the rotor windings will register on this meter. The motor is started, and when the rotor is energized, it locks into synchronous speed. As the current through the rotor is decreased, the rotor's magnetic field decreases. Watch the mark carefully. It moves backwards slightly as the current decreases. The rotor begins to lag. When the direct current is decreased too much, it pulls out of synchronization. Well, we just saw one way that the strength of the rotor's magnetic field affects the motor's operation. There's another way too. Since the rotor's field cuts through the stator, the rotor's field affects the phase relationship between voltage and current in the stator. This relationship determines the power factor of a motor. Power factor is a measure of electrical efficiency. When a motor, or any electrical equipment, operates at peak efficiency, voltage and current work together. They're in phase with each other. This is called unity power factor. At unity power factor, the motor uses a minimum amount of current to produce the greatest amount of work. Overexciting or underexciting the rotor windings causes current and voltage in the stator to go out of phase with each other. This causes current flow in the stator to increase. The motor uses more current to produce the same amount of work, so the electrical efficiency of the motor decreases. If we look at the sine curves of voltage and current in the stator of a synchronous motor, we can see how the rotor field affects their relationship. These sine curves show the relationship between current and voltage in the stator when the motor operates at maximum efficiency. Notice that current and voltage are in phase with each other. Now, if the current flowing through the rotor windings is increased, current and voltage in the stator go out of phase. The current cycle starts a little sooner than the voltage cycle. This causes current flow in the stator to go up, and the motor operates less efficiently. If current flowing through the rotor windings is decreased, the stator's current cycle begins a little later than the stator's voltage cycle. Current flow through the stator increases, and the motor again operates less efficiently. As we're going to show you, this phenomenon can be used to improve the electrical efficiency in your plant. But first, let's take a look at a demonstration of this effect on an actual synchronous motor. We'll use a synchronous motor that is operating at unity power factor. It's operating at maximum efficiency. Direct current is supplied to the rotor windings of the synchronous motor through this controller. We're going to use this rheostat to control the current going through the rotor windings. We'll be able to read the amount of current the rotor is using on this meter. The amount of three-phase current flowing through the motor stator is indicated on this meter. Watch the top meter closely. When we raise the current flow in the rotor, the AC meter shows an increase in stator current flow. That means the motor's operating less efficiently. As rotor current is decreased to its original value, the meter shows a decrease in stator current. Once again, the motor operates at unity power factor. Now this time, we'll decrease the current flow in the rotor. Watch the top meter. Even though we've decreased the current flowing through the rotor, the meter shows an increase in stator current flow. Again, the motor is operating less efficiently. We can therefore adjust the power factor of a synchronous motor by adjusting the amount of direct current flowing through the rotor windings. This power factor adjustment is an important advantage of synchronous motors. By adjusting the power factor of synchronous motors, the overall electrical efficiency of an industrial operation can be improved. How is that possible? Well, an industrial plant uses many induction motors, transformers, and other equipment that have a low power factor. They cause current to lag behind voltage. This causes an overall electrical inefficiency in a plant. Overexciting a synchronous motor counteracts this effect. Overexcitation causes current to lead voltage. That makes the synchronous motor less efficient, but it also causes the overall current to be more in phase with the overall voltage in the plant. Remember, the closer current and voltage are to being in phase with each other, the greater the electrical efficiency. So overexciting a synchronous motor can improve the overall electrical efficiency of an industrial operation. You may find that sometimes synchronous motors are used solely for this advantage. Power factor adjustment for improved electrical efficiency is an advantage characteristic only to synchronous motors. And this advantage makes a synchronous motor an asset to many industrial operations. So take the time now to review this information in your text. Make sure you understand the effects of load on a synchronous motor. Learn the effects of overexciting and underexciting the rotor windings of a synchronous motor. And make sure you fully understand power factor and power factor adjustment. In the last two segments, we talked about synchronous motor principles. In this segment, we're going to show you how the supply of direct current to the rotor windings of a synchronous motor is controlled. For our purposes in this segment, we'll be talking about synchronous motors that use the principle of induction to accelerate their rotors to a speed near synchronous speed. The control of direct current to the rotor windings of a synchronous motor is called field control. Field control does two things. It controls the amount of DC that flows through the rotor windings, and it controls when the rotor windings are energized. There are basically two ways to energize the rotor windings: through manual field control and magnetic field control. Manual field control uses a manual switch to open or close the circuit from the DC power supply to the rotor windings. When the operator determines that the rotor is turning close to synchronous speed, he closes the switch and energizes the rotor windings. A manual field controller, however, does not afford protection for a motor. If the rotor windings are not energized, or if there is a loss of direct current to the rotor windings during motor operation, the motor could be damaged. In both instances, the motor would continue to operate by induction. Since the amortisseur bars are designed to handle induction for only a short period of time, continued induction over a long period of time can cause them to be seriously damaged. At the same time, a manual field controller has no effective means to determine when the rotor windings should be energized. The operator must observe the rotor to determine if it's turning near synchronous speed. If the operator energizes the rotor's field too soon, the rotor of a synchronous motor would accelerate rapidly as it locks into the stator's rotating field. This rapid acceleration of the rotor could damage the motor or the equipment that the motor drives. To help prevent such damage to a synchronous motor, a more complicated field control system is commonly used, a magnetic field controller. The main function of a magnetic field controller is to energize the rotor windings when the rotor is close enough to synchronous speed so that damage to the motor or the equipment it drives does not occur. At the same time, a magnetic field controller protects a synchronous motor in the event that the rotor windings fail to become energized, or if there is a loss of DC current through the rotor windings during motor operation. A magnetic field controller uses electromagnetic switches to control the opening and closing of the circuit from the DC power supply through the rotor windings. Let's take a look at a simplified synchronous motor controller and see how it operates. The schematic of this controller can be divided into a stator circuit and a rotor circuit. The stator circuit contains 3 line leads, a circuit breaker, 3 overload heaters, and the stator windings of the motor. The rotor circuit contains the DC power supply, a number of relays and contacts, and the rotor windings. When the circuit breaker is closed, alternating current flows from an AC power supply through the stator windings of the motor. Closing the circuit breaker causes these contacts to close. At the same time, these contacts open. We'll see why that happens in a minute. As the stator field rotates, its magnetic poles sweep across the rotor, inducing an alternating current in the amortisseur bars of the rotor and the rotor windings. The induced alternating current flows through this part of the circuit. An inductor is part of this circuit. The inductor is connected in parallel with an AC coil. The AC coil is part of a component called a field frequency relay. The relay also has a DC coil in it. The main function of a field frequency relay is to control when the rotor windings should be energized. This drawing shows a typical field frequency relay. The relay has 2 coils wound around a core. Its contacts, which are connected to a circuit by these wires, are normally in a closed position. When both coils are energized, the contacts of the relay open and break the circuit. Neither one of the coils alone can open the contacts of the relay. Both coils must be energized before the contacts will open. In the control circuit, the field frequency relay is placed so that one of its coils is connected across the DC power supply. This coil is known as the relay's DC coil, and it continually receives a supply of direct current from the DC power supply. The relay's other coil is connected in parallel with the inductor in the circuit. Let's take a look at how the field frequency relay operates. As we said, when the circuit breaker is closed at motor start, these contacts in the rotor circuit close. At the same time, the field frequency relay contacts open. The reason that they open is that the stator field induces an alternating current in this part of the circuit. When alternating current flows through an inductor, there's a voltage drop across the inductor. The voltage drop across the inductor that's in parallel with the AC coil causes current to flow through the AC coil. The AC coil aids the already energized DC coil in opening the contacts of the field frequency relay. In a moment, we'll discuss why there's a voltage drop across the inductor. But for right now, let's take a look at 2 other components in the circuit. Resistors in this part of the circuit are used to limit the amount of alternating current flow. If the resistors were not placed in the circuit, alternating current flow would increase to the point where it would burn wires or cause damage to the insulation of the wires. Another component of this part of the circuit is a heater element for a thermal overload device. The heater element senses the amount of current flow through the circuit and is designed to open the circuit breaker if current flow persists for too long. Therefore, if induction continues to occur, such as would be the case if the rotor windings failed to be energized, the thermal overload device would operate to stop the motor. That protects the amortisseur bars from prolonged current flow that could damage them. Now that we've looked at the resistors and overload device of the circuit, let's return to the inductor and see why a voltage drop occurs. The voltage drop across the inductor is related to the frequency of the induced alternating current in the circuit. The frequency of the induced alternating current depends on the speed with which the stator's field sweeps across the rotor. The closer the rotor gets to synchronous speed, the slower the stator field sweeps across it. So the frequency of the induced current decreases as the rotor approaches synchronous speed. You may already know that as frequency decreases, inductive reactance decreases. So when the frequency of the induced alternating current is at maximum, such as it is at motor start, the inductive reactance of the inductor in the circuit is at maximum. That produces a large voltage drop across the inductor. The greater the voltage drop across the inductor, the greater the current flow through the AC coil will be. As the rotor accelerates closer to synchronous speed, the frequency of the induced alternating current decreases. The voltage drop across the inductor also decreases. That decreases current flow through the AC coil. The electromagnetic field of the AC coil, therefore, becomes weaker as the rotor approaches synchronous speed, and it is unable to aid the DC coil in holding the relay's contacts open. The contacts drop into a closed position. When the field frequency relay contacts close, the circuit from the DC power supply through the operating coil of another relay is complete. This relay is called a field relay, and its main function is to close the circuit from the DC power supply through the rotor. At the same time, the field relay opens contacts in this part of the circuit. That eliminates the components that are only needed when there is induced current flow through the rotor. There's still another relay in this synchronous motor controller, and that's a field loss relay. A field loss relay trips the stator circuit breaker if excitation current is lost during motor operation. When the field relay contacts are closed, direct current flows through the field loss coil. If direct current is lost, the coil is de-energized and trips the circuit breaker to stop the motor. That prevents continued operation by induction, which could damage the motor. Well, that is a lot of information to cover in one segment, to be sure. But magnetic field controllers are quite complex. Their complexity, however, helps to ensure a more precise application of direct current through the rotor windings of a synchronous motor. Their complexity also helps protect the motor from damage. The various components of the magnetic field controller shown here are discussed more fully in your text. So take the time now to review the text and make sure you fully understand field control of synchronous motors. As for any electrical equipment, it's an important part of your job to take good care of the synchronous motors and their controllers in your plant. Proper cleaning procedures and careful inspection for any signs of potential problems help keep synchronous motors and controllers operating at peak efficiency. In this segment, we're going to show you some preventive maintenance procedures for both synchronous motors and their controllers. First, we'll show you how to inspect an operating synchronous motor. Then we'll show you how to inspect a synchronous motor that's not operating. Before inspecting a synchronous motor that is operating, follow all your plant's safety procedures concerning operating electrical equipment. Be sure to remove any wristwatches, rings, or other accessories that might conduct electricity. Button any open shirt cuffs and make sure your clothing isn't loose enough to become entangled in moving machinery. Then listen carefully to the motor's sound. It should sound smooth and steady. An unsteady sound or an increase in noise may indicate that a problem exists. Place your hand along the stator frame to check for vibration and excessive heating. Vibration is often caused by bad bearings or an imbalanced rotor. Overheating is caused by excessive current flow or blocked air vents and can damage insulation. Be careful when touching near the bearings of the motor. A problem in this area can generate enough heat to seriously burn you. By using a flashlight and looking through the motor's protective screen, you may be able to see the stator windings. Examine the windings carefully. Look for discoloration, signs of burnt insulation, and dirt. After checking the stator windings, visually examine the motor's brushes, brush rigging, and slip rings. Take notice of the surface of the slip rings and check for grooving or discoloration. Also look for wearing of the brushes and sparking. Keep all your senses alert for any indication of a motor problem. Always be on guard for any unusual odors. An abnormal smell could be a sign of burnt insulation. Now, to inspect a motor more thoroughly, you're going to need to examine it when it's not operating. Even when inspecting a motor that's not operating, you want to be sure to take all necessary safety precautions. First, have the motor de-energized and make sure the AC power supply breaker is tagged in the off position and the DC power supply breaker is also tagged out according to your plant's procedures. After both power supplies are tagged in the off position, remove the motor screen so that the motor parts are accessible. The screen is there for your protection when the motor is operating, so never remove it unless the motor is tagged out. Next, use a voltage tester that has been checked for proper operation to verify that the motor is de-energized and hasn't any charge on it. Test line to line and line to ground at the slip rings of the motor. A 0 voltage reading for both indicates that the rotor is safe to work on. Then begin your inspection by examining the brushes and brush rigging. Make sure all the brushes touch their slip rings and are properly seated. Remove the brushes and carefully examine them for grooving, chipping, or any other signs that might indicate a problem. If you find a problem, loosen the brush's electrical connection and the brush can be removed from its holder. This brush is chipped, so it's necessary to replace it. As a rule of thumb, if any of the brushes are worn below 1/4 of their useful length, the brushes must be replaced. In some plants, when any of the brushes require replacing because of excessive wear, all of the brushes are replaced. Follow the procedures used in your plant. For proper brush performance, all brushes should be seated to the curvature of their slip rings when they are replaced. Improper seating can cause sparking and overheating that can damage both slip rings and brushes. To seat the brushes, a piece of sandpaper is placed between the slip rings and brushes. The sandpaper is then moved back and forth along the underside of the brushes. The slip rings also should be carefully inspected. Check for grooving, discoloration, and contamination. Dirt and other contamination could cause a poor conducting path. Here we have some minor discoloration, and so we use an approved solvent and a non-abrasive wiper to clean them. If you find grooving or any other serious problem, report it to your supervisor. A common preventive maintenance test for a synchronous motor is the insulation test. This test is usually done on both the stator and the rotor. In this demonstration, we're going to test the rotor. The instrument used for this test is a meg-ohm meter. Before beginning an insulation test, double-check to make sure the motor is tagged out according to plant procedures, and make sure it's de-energized. Then lift the brushes to isolate the rotor from its DC power supply. Before beginning the insulation test, the meg-ohm meter should be tested. Using proper procedures, make sure it will indicate infinite resistance and zero resistance. Next, attach a clip to the motor's shaft and connect the meg-ohm meter's ground lead to the clip. Then attach another clip to the shaft and connect the line lead to it. Operate the meg-ohm meter. It should indicate zero resistance. This means the ground connection is good. Now attach the line lead to one of the slip rings. The meg-ohm meter is operated for 1 minute. As a rule of thumb, a reading of at least 1 megohm for each 1,000 rated volts with a minimum of 1 megohm should be indicated on the meg-ohm meter. If it isn't, there may be a problem with the insulation. The reading here is infinite resistance. This indicates that the insulation is in pretty good shape. The rotor receives a charge from the meg-ohm meter, so it must be discharged at the end of the test. In most plants, the readings from insulation tests are recorded and evaluated to see if a trend is developing. In this way, insulation deterioration over a period of time can be detected. As we've said, the insulation test can also be taken on the stator of a synchronous motor. The procedures for the stator are similar to those for the rotor. The main difference is that to test the stator, the motor leads are clipped together and the 3 phases are tested together. Besides taking good care of a synchronous motor, it's important for you to properly maintain its controller. The preventive maintenance procedures for a controller should only be undertaken when a controller is de-energized. So first, have the controller de-energized. Have both the AC and the DC power supplies tagged off. By loosening the knobs at the side of the controller cabinet, the cabinet can be opened. Then the controller must be tested to make sure it's completely de-energized. A voltage tester, which has been checked for proper operation, is used to test the controller. The voltage tester probes are placed at each line of the DC power supply, and a reading is taken. The voltage tester should indicate that there is no power. Then each line is tested to ground. Again, there shouldn't be any indication of DC power. Next, the AC power supply leads are tested. Readings are taken between all phases. Then each of the 3 phases are tested to ground. Zero readings for all parts of this procedure indicate that the controller is de-energized and safe to work on. Once you're sure the controller is de-energized, it should be thoroughly cleaned. Here we're using low-pressure compressed air to blow the controller free of dust, dirt, or other contaminants. It's a good idea to ask your supervisor what the approved method is for cleaning controllers in your plant. And remember, when cleaning a controller, follow all your plant's safety procedures. Don't forget to use proper protective equipment when working with compressed air. It's important to clean the controller as completely as possible. Dust, dirt, or other contaminants may contain conducting materials that can cause short circuits and grounds inside a controller. Dirt may also prevent contacts from closing properly, and an incomplete circuit could result. Once the controller is cleaned, examine its wiring. Look for frayed or cracked insulation. Make sure all of the controller's connections are tight. Then check all controller relays. Manipulate each relay by hand and make sure they are operating properly. Check the surfaces of the contacts and make sure they are clean and making good contact. Examine the operating coil of each relay. Look for any signs of overheating, such as damaged insulation. Once you've carefully cleaned and inspected the controller and have replaced any components necessary, have the controller energized, its tags removed, and return it to service. It's very important for you to properly maintain the synchronous motors and controllers in your plant. So before going any further, take the time to learn these preventive maintenance procedures. When a synchronous motor or its controller breaks down, it'll be your responsibility to find out what is causing the problem and correct it. In order to do that, you're going to need to know what types of problems to look for and how to test both the controller and the motor for them. We'll begin by talking about testing a controller. Before beginning any testing on a synchronous motor's controller, it's important for you to follow all your plant safety measures. Make sure that both the AC and the DC power supplies are tagged out, and make sure that the controller is completely de-energized. There are basically three types of problems that occur in controllers: grounds, opens, and shorts. A ground is an accidental current path from the conductors in a circuit to ground. The test procedures for grounds are the same general procedures as the insulation testing described in the previous segment. A meg-ohm meter is used to test the resistance of the circuit's insulation. Remember, as a rule of thumb, a reading of at least 1 meg-ohm for each 1,000 rated volts with a minimum of 1 meg-ohm should be indicated on the meter. If it isn't, a ground may exist in the component. Now, to test a controller for both opens and shorts, a multimeter will usually be used, and a resistance reading is taken across the component in question. An open is a break in a current path. When an open occurs, current is unable to flow through a circuit. Therefore, when an open exists in a component, high resistance will register on a multimeter. A short, though, is an accidental current path of low resistance. A short in a component will register low resistance on a multimeter. The low resistance of a short causes high current flow that can cause overheating, circuit breakers to trip, and fuses to burn out. Let's take a look at an example of testing a component for opens. We'll test the field relay coil of this controller. When we test the field relay coil for opens, we will also be testing it for shorts. After the controller has been completely de-energized and tested to make sure that it is de-energized, the multimeter is set to its resistance scale and zeroed. Then one of the electrical connections of the field relay coil is disconnected. The multimeter probes are placed at each electrical connection point of the coil, and a reading is taken. A high resistance reading on the multimeter indicates that an open exists in the coil. A low resistance reading indicates that there's a short. Here, the reading is infinite resistance. An open exists in the coil. Now, if the reading had been very low, it would have indicated that a short may exist in the relay coil. But shorts can't always be detected by a multimeter. Sometimes the amount of decrease in resistance caused by a short is so small that a multimeter just isn't sensitive enough to detect it. If that were the case, a more sensitive resistance measuring instrument might be needed to verify that a short was causing the problem. Once it has been determined that a component does have a problem, then the bad component must be replaced by a new component of the same size and rating as the old one. Before installing a new component, it's a good idea to test it and make sure that it's good. After correcting a controller problem, the tags can be removed and the controller can be energized. Then a test run of the equipment should be made to make sure that there aren't any other problems. Grounds, opens, and shorts are also common problems found in synchronous motors. These problems can cause malfunctions in both the stator and the rotor of a synchronous motor. Before testing a motor for these problems, the motor must be de-energized and then tested to make sure that it is completely de-energized. Next, the motor should be visually examined for any indication of where the problem might be located in the motor. After visually examining the motor, the protective screen can be removed and the motor can be tested. The techniques for testing the stator and the rotor for grounds, opens, and shorts are basically the same. So for our purposes in this segment, we'll use the rotor of a synchronous motor to demonstrate the testing procedures for each problem. To test a rotor for grounds, use the same test procedures that we showed you earlier for testing rotor insulation. Remember, you use a meg-ohm meter and test from one of the slip rings to ground. The meg-ohm meter is operated for a period of time and a reading is taken. The reading is compared with previous readings taken under the same conditions to see if a trend is developing. Basically, testing for opens and shorts in a rotor of a synchronous motor is similar to testing for opens in a controller. A multimeter is used to test the rotor for continuity, that is, a complete circuit through the rotor windings. A high resistance reading across the slip rings of a motor indicates that an open exists in the rotor. A short, though, will register a low resistance reading on the multimeter. However, it may be difficult to detect a short, so it's usually a good idea to first eliminate grounds and opens as a cause of the problem. Once they're eliminated, you can be fairly certain that the problem is a short. In some cases, a more sensitive resistance measuring instrument would be used to verify that a short existed. Let's take a look at an example of testing a rotor for opens and shorts. To test the rotor for these problems, the rotor must first be isolated from its DC power supply. This is done by lifting the brushes from the rotor. Then a multimeter is used to measure the resistance through the rotor circuit. Before testing the circuit, the multimeter is set to the proper resistance scale and zeroed. The multimeter test probes are then placed on the slip rings, one on each slip ring, and a resistance reading is taken. The reading here is infinite resistance. This high resistance reading indicates that the rotor has an open. When a problem is detected in a rotor, the rotor must be repaired. But repairing a rotor can be a major job, and it is usually not done by an electrician in the plant. Most plants send their motors to a specialist when they must be repaired. The electrician's job is usually limited to finding the problem. It's extremely important for you to know how to test the synchronous motors and their controllers in your plant. Testing these motors and their controllers helps you detect malfunctions that can prevent the plant from operating effectively. So take the time now to review this information in your text and make sure that when it's time for you to tackle a motor or controller problem, you'll be ready.